pipelining class for CIS250 at Pima Community College. So for today's class, what we're going to be doing is going over pipelining. Now, all pipelining is basically breaking up processes that go through the processor into smaller units so you can actually put more than, you can basically run them in parallel. And so the definition of processor pipelining, or just pipelining, is instruction level parallelism on the processor. Essentially, you can have multiple processes or multiple commands running on the processor at the same time, and so you can get a little bit faster throughput. And so, like I say, you break up an instruction into smaller parts, which we'll define later, so multiple instructions can be on the processor at the same time. So basically, you have little subunits on the processor running at the same time. And so pipeline executes multiple instructions in parallel and runs them concurrently. So basically it means there might be different branches on the processor where they can kind of run at the same time and go through. It's called pipeline because one's right after another on the processor. So you can have, depending on the length of the processor, you can have 5 or 6 different commands running at the same time. And so basically, like what this image shows, like with instruction 1, you have a pipeline stage where you have essentially 5 different instructions going at the same time, and then the green line is where they are in the pipe at one point. So instruction 1 is at the mem portion, so it's memory dumping at the same time. Instruction 2 is going to be executing. Instruction 3 is going to be decoding. Instruction 4 is going to be at the moment it's going to be instruction fetching, and then instruction 5 is waiting to be go on, so it'll be the next one to go on. So at clock cycle 4, basically there's 4 different processors on there. And so in the classic RISC pipeline, there's basically 4 types of items. You see fetch, which you saw on the previous one, is IF. It gets the instruction, decodes it, extracts the command, and basically kind of, when it extracts the command, it takes it down the path that it needs to go. So there's going to be different paths for integer commands, as well floating point commands, and also sometimes there'll be different paths for multiplication and division as well along the integer type of commands. So basically you have different paths for the ALU and for integers and the FPU for floating points. Then you execute, means you basically compute the values, you do the addition, multiplication, whatever. And memory access is you read and write stuff to the memory, and then you write back, and that's where you put the results into the register. So you have multiple steps. Generally, the memory access, you'll see in the next slides, memory access and write back are going to be combined together. So we basically only have 4 processes: fetching, decoding, executing, memory access, and write back. All the same thing. So the classic structure is you have the green command is the green block in this case is going to be the first instruction. Purple is going to be the second. The third one of blue is going to be the third instruction, and the red one's going to be the fourth one. So during the first clock cycle, the green instruction, the first instruction, is you're going to fetch instruction from memory. Now the second one is going to decode. With second cycle, we're going to decode the instruction from memory, and at the same time, the next commands you're going to fetch the instruction set. And then the third step is you're going to execute it. So whatever the decoded instruction set is, it's going to run it. So basically, maybe pull some stuff from the registers, run it, so on and so forth. While at that time, the second instruction is getting decoded, and the third one's getting fetched from memory. So at this point, we have 3 instructions on the chip running at the same time. And then as you get to the fourth one, you get to the write back memory access. So that's going to be, that instruction is going to be stopped. The purple one, the third instruction is going to be running. So in that case, we have 4 instructions on the purple set. Now, after that, the green one's done. And so you're going to go forth. And while it may not seem obvious, you will get faster performance this way. However, what happens if halfway through the instruction set, you notice that there's going to be a decision, like a comparison or an if statement or a while loop or something like that, where it's going to have to change up? In that case, you get a bubble. And basically a bubble is a skip step. So you can kind of see in this instance here where this decode means, okay, well, we notice here that there's going to be, it's doing a comparison, so it's going to do a jump next. So we need to figure out where we're going to jump next before we do this. So these steps are going to be stiff. So we get a little bit slower throughput. And then when it realizes where it's going to jump, the purple one goes on and starts decoding, so on and so forth. And so basically you have to have elegant ways of handling stuff being bumped, or due to commands, or you have a interrupts and stuff like that. And so essentially, you have to have basically this is what the point is showing is having less kind of branch unknown branches where you don't know where you're going to go helps makes the processor run a little bit faster. So that's all I really have for the pipeline discussion, but think about a couple other things. So how would you design a pipeline processor to handle branches? And then also, how would you speed up the passing of data? These are discussions we'll have next week in class, but I just want you to think about these as we go forward. So that's all I have for you.